Hello guys, and welcome to another calculus video. In this video we're going to be doing another live solving session. We're going to be solving pretty much the same thing as last time, Cambridge integration problems from 2022 to 2023 and the round 2 problems. Feel free to skip around because I'll probably make a lot of mistakes and be kind of sitting there thinking for a while. Watch whatever part you want, and I hope you guys enjoy the video. So let's go ahead and get started. So problem 1 here is going to be integral integral from 0 to 1 of 1 over x minus cotangent x dx. So I think this one we're just going to integrate normally, and then we're going to have to do a limit. So this is going to be a natural log of x minus integral of cotangent x is ln sine of x, sine x, evaluated at 1 and at 0, and really we're talking 0 plus, right? So at 1, we're just going to have minus ln sine of 1. And then at 0, we're going to have limit as x goes to 0 plus of ln x minus ln sine of x. And we can just combine this into one big natural log. So we just go ahead and erase. We're going to have ln x over sine of x. And of course, as the limit as x goes to 0 plus, this is a really famous limit. This just goes to 1, and so overall this just goes to 0, and our answer is negative natural log of sine of 1. Let's go ahead and move on to the next problem. We check my answer also on the answer key here. Yep, that's correct. All right. Oh, this one's a fun one. We have integral of x to the n over 1 plus x squared over 2 plus x cubed over 6 all the way to x to the n over n factorial dx. So this is a bit of an interesting problem. The bottom looks like e to the x here, so that's what I'm thinking is definitely going to be part of the answer. So if we call this function like, I don't know, f of x or something, we know that limit as n goes to, or I guess fn of x, limit as n goes to infinity of fn of x equals e to the x, so that could be kind of helpful. I'm thinking maybe here, the defining feature of e to the x basically is that the derivative of e to the x is just e to the x. So if we differentiate this function, we're going to get something pretty similar. So if we notice that d over dx fn of x equals the derivative with respect to x of the sum from k equals 0 to n of x to the k over k factorial, which is equal to the sum from k equals 1 to infinity of x to the k minus 1 over, not to infinity, to n, sorry. N over k minus 1 factorial equals the sum from k equals 0 to n minus 1 of x to the k over k factorial equals fn minus 1 of x. So essentially, when we differentiate, this last term basically will just disappear. So we can use that because on the top here, all we have is that last term. So let's go ahead and make some space to do the actual calculation here. So if we go ahead and multiply by n factorial out here and divide by it in here, so we're going to have x to the n over n factorial, we know that x to the n over n factorial equals f sub n of x minus f sub n minus 1 of x, since that's the only term that's different, right? So we have n factorial equals the integral of f sub n of x minus f sub n minus 1 of x over f sub n of x dx. And we know that d over dx of f sub n of x equals f sub n minus 1 of x. And so that's going to help us. So this left part, we're just going to have n factorial times x, because that's just 1. And then we're going to be subtracting the integral of the derivative of this function over this function, so that's just going to be n factorial times natural log of 1 plus x squared over 2 dot 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 x to the n over n factorial. That's a pretty cool one. I think I feel like I've seen this problem somewhere before, but I'm not entirely certain. But that's a pretty cool, interesting problem that we have right there. Let's move on to the next one and check our answer also, of course. Yep, that's the correct answer. Oh, I forgot the plus c, but that doesn't really matter. Okay, the next one is kind of interesting. So we have the integral from 0 to 1 of the integral from 0 to z of ln, let's see, 1 minus u over u du dz. So immediately I'm trying to think of sort of using this and exchanging the bounds of integration, but I'm thinking here that we might not actually need to do that. So I'm going to talk about the special function, the die logarithm, or li2 of z. It's equal to the sum from n equals 1 to infinity of z to the n over n squared. And it's also equal to the integral from 0 to z of negative ln 1 minus u over u du. So we can go ahead and just replace this inside with negative li2 of z. So we have integral from 0 to 1 of negative li2 of z dz. And then we're going to go ahead and just make that a summation, right? So negative sum from n equals 1 to infinity of 1 over n squared times the integral from 0 to 1 of z to the n dz, which is, of course, just 1 over n plus 1. So we're just going to have this summation right here. And in order to solve this, let's just do some magic partial fractions right here. So I'm going to add n and subtract n. So we're going to have negative sum from n equals 1 to infinity of 1 over n squared plus sum from n equals 1 to infinity of 1 over n times n plus 1. So this is going to be telescoping. This just is negative pi squared over 6. I can't write here because that's where the PowerPoint thing is, so negative pi squared over 6. And this one, if we go ahead and do this telescoping series, it's going to be sum from n equals 1 to infinity. Partial fractions is going to be 1 over n minus 1 over n plus 1. Does that make sense? Yeah, that works. And so we're just going to have 1 minus 1 half plus 1 half minus 1 third dot 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 up to infinity plus 1 over n minus 1 over n plus 1. So this is just going to go to 0. These are all going to cancel with stuff, and we're just going to be left with 1. So the answer should be 1 minus pi squared over 6. Beautiful. Whew. Looks like we have some easier problems this time because they're not taking quite as long. Let's go ahead and check the answer. And that is in fact the answer. All right, next integral. Now we are going to have, okay, the integral, this one looks fun. The integral from 0 to pi over 2 of 1 over cosine x plus sine x all squared dx. So I think there's a few different ways to do this. I'm going to go with the easiest way. So there's a few different ways. One way that you can do this is you know that sine x plus cosine x equals square root 2 sine x plus pi over 4, and then you'll just end up with cosecant squared of x, which is super easy to integrate. But I think the easiest way in this case is actually just to multiply by secant squared on the top and bottom, because then we're going to end up with secant squared on the top, which allows us to substitute u equals tangent squared. And so on the bottom, we're going to just have 1 plus tangent x dx. This is just du, where u is tangent x, so we have integral from 0 to infinity of 1 over 1 plus u squared du, or negative 1 over u plus 1 evaluated at infinity and at 0. So that's just going to be 1, and that's our answer. Let's go ahead and check. Yeah, the answer is 1. All right, that one was pretty straightforward. Let's go ahead and work on the next one. So the next integral is kind of interesting. We have integral from 1 to infinity of negative 1 to the floor of x. I think it's floor of x, right? Yeah, over x dx. So this we're just going to have to split up into infinitely many integrals. So we're going to split this up into the sum from n equals 1 to infinity of the integral from n to n plus 1. So we're just going to end up with the same integration region of -1 to the floor of x over x dx. However, floor of x, when x is between n and n plus 1, it's just going to be equal to n. So it's going to be -1 to the n here. And so we can just bring that out of the summation, right? This is just going to be 1. And so we're going to have sum from n equals 1 to infinity of -1 to the n times ln n plus 1 minus ln n. Ooh, that's going to be interesting. Okay. Where do I even go from here? Let's split it up into the even and odd terms, because that's maybe going to make it a little easier. So for the even terms, we have the sum from n equals 1 to infinity of the -1 to the n is just going to be 1, so it doesn't really matter, this parentheses here. So let's do ln 2n plus 1 minus ln 2n, right? Plus another summation, so this one's going to be a sum from n equals 0 to infinity, and we're going to have a negative sign because now all our -1 to the n are going to be negative. Oh, I accidentally just moved a slide here. Okay, we have a sum from n equals 1 to infinity of ln 2n plus 1 minus ln 2n minus summation from n equals 0 to infinity of ln 2n plus 2 minus ln 2n plus 1. Okay, and I should note that both of these are going to infinity at the same rate, since we're just taking even and odd terms. So every time we add a term to one, we add a term to the other right after. So I think we could just... Wait, does this even converge? I'm not sure this converges. Did I screw up somewhere? Huh. Okay, well, if we reorganize everything, we're going to have the sum from n equals 1 to... let's just take out the first term here. So let's write this as the sum from n equals 1 to infinity. And we'll just have to subtract from these. So this will just become 2n, and this will become 2n minus 1. Okay, that helped us a little bit. Not too much, though. So now we're going to have sum from n equals 1 to infinity of ln 2n plus 1 times 2n minus 1 over 4n squared equals the sum from n equals 1 to infinity of ln 4n squared minus 1 over 4n squared. Okay, I think this does help us because now we have the sum from n equals 1 to infinity of 1 ln 1 minus 1 over 4n squared. Did this help us at all? I don't think it did. Huh. This is interesting. I'm not really sure how to evaluate the summation. Can we expand this as another series? Is that going to help us out? That's not going to help us out. Is it some sort of Wallace product? Yeah. I think this might be related to the Wallace product. I'm going to have to check that out real quick. Let me check what the Wallace product is, because I think it's related to that. Wallace product. This is often how integrals go. Yeah, so the Wallace product says that pi over 2 equals the product from n equals 1 to infinity of 4n squared over 4n squared minus 1. So that means 2 over pi equals the product from n equals 1 to infinity of 4n squared minus 1 over 4n squared. Then when we take the natural log, we get ln 2 over pi equals, now each of these we separate so it becomes a summation, n equals 1 to infinity of ln 4n squared minus 1 over 4n squared. Yeah, so whenever you see whenever you see either adding natural logs of even numbers and subtracting those of odd ones or something like that, or if you have multiplying even numbers and dividing by odd ones, think the Wallace product, because that is where that comes from. So our answer here is actually natural log of 2 over pi. So that's sometimes something that will happen. So obviously if I was participating in the competition here, I wouldn't have gotten this problem just because I don't know what the Wallace product is by heart. I guess I could have used the infinite series for sine x, I think. But anyway, so yeah, so that's something to keep in mind. Know all the identities you can, because a lot of them are going to pop up on weird b's like this. So that's our answer right there. Let me just go ahead and check. Yeah, that is the correct answer here. So let's go ahead and move on to the next problem. Okay, we have integral from 0 to infinity of 1 over x plus square root x squared plus 1 squared dx. So there's two options here. Option 1 is x equals tangent theta, because then this will just become secant theta. And option 2 is x equals sine h of t, because then this will just become cosh. So I think the sine h one is actually going to work out a little bit better for us. So because we're also going to end up integral from 0 to infinity right here, so that means that dx is going to be cosh of t, right, dt. So we're going to have cosh of t over cosh of t plus sine h of t squared dt. So this looks like a pretty similar integral to what we had before. Now if I multiply by sec squared, we're only going to have one hyperbolic secant on the top, which won't help us out. Oh, we can maybe get it all in terms of 1? Let's think. Well, let's try our other substitution and see if that's going to make things any easier for us. So that means that dx is going to be secant squared theta d theta. So we'll end up with integral from 0 to pi over 2 of secant squared of theta d theta over tangent theta plus secant theta squared. And if we just multiply by cosine squared on the top and bottom, we're going to just get 1 on the top, and we're going to get sine theta plus 1. Seems like it might be a little bit easier. If we multiply that out, is that going to make things easier for us? We might just have to do some nasty wire stress substitution here. Yeah, let's just do the wire stress substitution. So u equals tangent of x over 2. 2 over u squared plus 1 du equals dx. And sine theta equals 2u over 1 plus u squared. So after we make the substitution, tangent of x over 2, we're just going to end up integrating, or tangent of theta over 2, I should say, theta everywhere here. We're going to end up integrating from 0 to 1. We're going to have 2 over u squared plus 1 squared. No, that's not what's going to happen. We're going to have, okay, we're going to multiply by u squared plus 1 on the top and bottom. So 1 plus u squared here. And then on the bottom, we're going to have u squared plus 1 plus 2u. plus 1 squared, right? So u plus 1 to the 4th on the bottom. All right, that's a pretty simple integral to do. So we're just going to have to do 2 integral from 0 to 1, u squared plus u minus u plus 1, right? Du over u to the 4th plus u plus 1 to the 4th. So we have 2 integral from 0 to 1, and then we're going to end up with just u over u plus 1 cubed. Let's do minus u minus 1 plus 2. So minus 1 over u plus 1 cubed plus 2 over u plus 1 to the 4th du. So we're also going to plus 1 minus 1, so this is going to become minus 2. And then we're going to end up with just, here we're going to have 1 over u plus 1 squared. And then we can finally plug everything in. So we're going to have 2 times negative 1 over u plus 1 plus 2 over u plus 1, or I guess just 1 over u plus 1 squared, minus 2/3 u plus 1 cubed, evaluated at 1 and at 0. So we're going to have 2 times negative 1/2 plus 1/4 minus 1 over 12 plus 1 minus 1 plus 2/3. All right, that's absolutely nasty. So let's see if we can simplify this. So this is just going to become negative 1/4, right? Negative 1/4. Those are going to cancel. So negative 1/4 minus 1/12 plus 2/3. So let's write this all in terms of twelfths. So we're going to have 2 times 3 minus 1 plus 8 over 12. So it's going to be 10 over 12. Oh, this is negative, minus 3. So it's going to be 4 over 12, so our final answer is going to be 2/3. All right, let's go ahead and check that answer. So it's a pretty straightforward one, but it's just a lot of work. So this is the one that, they're just trying to kill time, right? So let's go ahead and check the answer. And yes, it is in fact 2/3. So next problem. All right. We have integral from 0 to 1 of ln x, ln 1 plus x squared. So I'm thinking if we expand this as a power series, and then we just have this multiplied, and we can pretty easily solve it. So let's go ahead and do that. Sum from n equals 0 to infinity. Wait. So ln 1 plus x equals negative sum from n equals 1 to infinity of negative 1 to the n, x to the n over n. That's just the way I'm going to think about it. So I'm going to, let's do it that way. All right, so this is what we have, dx, and integral from 0 to 1 of x to the a ln x is just negative 1 over 1 plus a squared. So this negative sign is going to come out. We're going to have the sum from n equals 1 to infinity of negative 1 to the n over n times 2n plus 1 squared. All right, so we're going to have some g in here. Let's do partial fractions. I really don't want to do partial fractions. So 1 over n, 2n plus 1 squared equals a over n plus b over 2n plus 1 plus c over 2n plus 1 squared. Alright, using the cover-up method, we can immediately see that A equals 1, and that C equals -2. And now we just need to solve for the other one. So if we go ahead and multiply everything out, let's just solve for our n squared term. So that's going to be 4a plus, oh wait, that doesn't actually help us for solving for b. Let's solve for our constant term. So that's going to be a that doesn't help us either. Let's solve for our n term. So our term with n in it is going to be 4a plus 1b plus c equals 0. So that's going to be 2 plus b equals 0, or b equals -2. So we're going to have sum, I can't draw a sum today, sum from n equals 1 to infinity of -1 to the n over, yeah, -1 to the n times 1 over n minus 2 over 2n plus 1 squared minus 2 over 2n plus 1. And let's go ahead and cancel it, get rid of all of this other stuff because it's kind of in the way here. So we don't need all of this. Let's go ahead and solve our summation. I'm kind of worried because it's starting to look like the summation might end up with a positive number when our answer should be negative. So let's just go ahead and make sure that that doesn't happen. So we're going to have sum from n equals 1 to infinity of -1 to the n over n. Now this one is super easy. This just looks like it's going to be negative ln2, I think. Yeah, so our first part of our answer is negative ln2. And then after that, we have sum from n equals 1 to the infinity of -2, -1 to the n over 2n plus 1 squared. So this just is going to be some form of g. We're just missing the first term. So it's -2 times -g plus 1. So that's what this one is. So we're going to have plus 2g minus 2. And then our, wait. Wait, no, that can't be right because oh no, it's just g minus 1 here. This is g minus 1. Yeah, sorry about that. G minus 1. So we're going to have -2g plus 2. And for our last one, we have sum from n equals 1 to infinity of, I'll put the -2 out there, -1 to the n over 2n plus 1. And so this is going to be -2 times -pi over 2, or pi over 4, sorry, and then we're going to have plus 1, I think. That looks like it should be right, because we're missing that first term again, and it's all negative. So that's what it should look like. No, I guess it's 1 minus pi over, or it's pi over 4 minus 1. So we're going to have minus pi over 2 plus 2. So it's going to be negative ln2 minus 2g minus pi over 2 plus 4, which does not seem like it should be negative to me, but whatever. Let's go ahead and check the answer. It's probably close. Yeah, that's actually the exact correct answer. I'm surprised I got that, to be honest. So yeah, that's the answer right there. Pretty interesting integral right there. Let's go ahead and move on to the next one. We're at integral 8 of 10 now, so hopefully they should be getting a little bit more difficult. All right, we have, okay. Integral from 0 to 2 pi of sine of 24x over sine of x. Okay, I hate these types of integrals, I'm going to be honest. I hate them because it's just like, either there's some really obscure trick that you have to know, or you just have to brute force it all the way through. So first I'm going to try and check to see if maybe we have some like even odd situation going on here. So I'm going to try to make this like be in the middle. So I'm going to sub u equals pi minus x. So we're going to have, we're going to be integrating from negative pi to pi. And then sine of 24 pi minus 24x is just negative sine of 24x. Right? And then sine of x is just going to stay the same. So we're going to have sine of x. So that didn't really help us dx, right? Did it? Huh. What happens if I sub u equals pi over 2 minus x instead? We're now going to be integrating from negative 3 pi over 2 to pi over 2. But we're going to have negative sine of 24x. So we're going to have 12 minus 12 pi minus x, right? On the bottom we're going to have cosine x. Yeah, that didn't help us, did it? Okay, let's just go ahead and brute force it. So we're going to repeatedly apply our double angle identity. So we're going to get integral from 0 to 2 pi of 2 sine 12x cosine 12x over sine x dx. And once we apply that a few more times, we're going to get integral from 0 to 2 pi of, let's put the cosines in front. So cosine 12x cosine 6x cosine 3x sine 3x, and then it's going to be 2, 2, 2, so 8, and all over sine of x dx. Now this one we need to expand as 4 sine of x minus 3 sine cubed of x, I think. I believe that's how it expands. Maybe it's the other way around. 3 sine of x minus 4 sine cubed of x, I believe. I'm just checking it for a few different values just to be sure. Yeah, so this is actually what it is. So we're going to end up with two different integrals here. We're going to have integral from 0 to 2 pi of 24 cosine of 12x cosine of 6x cosine of 3x dx minus 32 times the integral from 0 to 2 pi of cosine 12x cosine 6x cosine 3x sine squared of x dx. And this is, see why I hate these types of integrals, because they just go on forever. So let's let this be I1 and I2, right? The good thing is a lot of these integrals will just end up going to 0, which is nice. A cool thing that we know is that we're going to have to use some identities here, but a useful thing is that when you're integrating over the entire period or over multiple periods for cosine x or sine of x, it's just going to be 0 because it oscillates perfectly. So integral from 0 to 2 pi, let's combine these two right here and use an identity. So it's going to be like 1/2 cosine a plus b plus 1/2 cosine a minus b, I believe. Yeah, that should be it. So we're going to get 12 cosine 18x plus cosine 6x. Right? That should be correct. And then cosine 3x, of course. And so the integral of cosine 6x times cosine 3x from 0 to pi should just go to 0, if I'm correct, because if we go ahead and expand those again, we're just going to end up with some other multiple of cosine, and so will this one. So this actually completely just goes to 0. So that's nice. So now we have negative 32 integral from 0 to 2 pi of cosine 12x, blah, 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 all that stuff. Cosine 12x, cosine 6x, cosine 3x, and I'll go ahead and expand that sine squared of x in a more easy to use manner. So we're going to have 16, 1 minus cosine 2x dx. I think this one should also go to 0, no? Okay, well we know that this part multiplied by that goes to 0 because we did it before. So we could just write this as positive 16 and then cosine 2x right here. Yeah, this should just go to 0. Yeah, I'm going to go ahead and take a guess and say that it goes all the way to 0. Let's go ahead and check the answer key on that. Yeah, it says it does go to 0. So that's a nice trick to know. If you have like cosine ax, cosine bx, integrated from 0 to 2 pi dx, where a and b are integers, and a is not equal to b, and a is not equal to negative b, obviously, then it just goes to 0 because you can expand it using the identities, and then you integrate it and it just goes to 0. And so that's a really useful tool because whenever you have a bunch of these that are all like chained together and you can't add or subtract any of them to make one of the other numbers, then you're just going to end up with a bunch of chains of this which all go to 0. So that's actually an interesting integral. So I actually like that one. So let's go ahead and move on to problem number 9, I believe. All right, problem number 9 here. Ooh, okay. Integral from 0 to infinity, ln 1 minus x plus x squared, I believe. Yeah. Over 1 plus x squared. Oh, okay, I see what we're going to have here, ln x dx. So whenever you see natural log, polynomials, 1 plus x squared on the bottom, that kind of stuff, and you're integrating from 0 to infinity, first thing to think is x equals 1 over u. Dx equals negative 1 over u squared du. So we're going to still end up integrating from 0 to infinity. Then we're going to have natural log of 1 minus 1 over u squared, or 1 over u plus 1 over u squared over, we're going to take this from the differential and combine it with this to just make this 1 plus u squared again. Then we're going to have negative an ln u on the bottom du. And so this, we just rewrite u squared minus u plus 1 over 2, or over u squared, sorry. So we're going to have, let's let this equal I. We're going to have negative integral from 0 to infinity, ln u squared minus u plus 1 minus 2 ln u all over 1 plus u squared ln u du. So we have I equals, and then this part right here is just negative I with this also. I equals negative I plus 2 integral from 0 to infinity of 1 over u squared plus 1 du. So that means that 2I is going to equal pi, or I equals pi over 2. So yeah, another one of those cheap tricks that you always have to remember. And that is, in fact, the correct answer. All right, last integral right here, number 10. This one looks a little bit more fun. Hopefully it's a little bit more difficult. We have, okay, integral from negative infinity to infinity, tan inverse of e to the x, hyperbolic tangent of x over 2 over cosh of x times x. I believe that's it. Yeah. So let's just write everything here in terms of e to the x, and that should hopefully make it a lot easier. So this is already in terms of e to the x, but on the bottom, this cosh of x is just e to the x plus 1 over e to the x over 2. And tan h of x over 2 equals e to the x over 2 minus e to the negative x over 2 over e to the x over 2 plus e to the x over 2, and multiply by e to the x over 2 on the top and bottom, and you get e to the x minus 1 over e to the x plus 1. Right? Yeah. So that's also in terms of e to the x. And I think we can just sub u equals e to the x here, probably. Let's see what happens if we try that. What happens if we sub u equals negative x instead? Oh, yeah, okay. I think first we're going to sub u equals negative x. So let's rewrite this back in terms of cosh x here. Okay, so we're going to sub u equals negative x, and so what we're going to end up with is the integral from negative infinity to infinity of tan inverse of 1 over e to the x, or e to the negative x. Hyperbolic tangent is just going to become negative, right? Negative hyperbolic tangent of x over 2. And then we're just going to have cosh of x is going to stay the same, and x is going to become negative, so that's going to cancel with that other negative sign. So x cosh of x dx. And this is going to help us a lot because tan inverse of 1 over u equals cot inverse of u equals pi over 2 minus tan inverse of u. So if we let this equal I, this is just pi over 2 minus tan inverse of e to the x, right? So this is also equal to I. So if we add both versions of I together, we get that 2I. This part is going to cancel with this part, right? So 2I is going to equal pi over 2 times the integral from negative infinity to infinity of tan h x over 2 over x cosh of x over cosh of x dx. All right, so that's one part dealt with. Now let's go ahead and just sub u equals e to the x and see what happens, because I'm interested on how we're supposed to deal with that. So we get pi over 4 here because it's going to be easier. Let's go ahead and make some space here, so I'm going to erase the rest of this. Alright, so when we sub u equals e to the x here, we're going to get I equals pi over 4, integral now from 0 to infinity of u minus 1 over u plus 1 over u plus 1 over u. We can multiply by 2 because of that cosh, right? So this just becomes pi over 2. And then we're going to have ln u, and then 1 over u. Huh. Interesting. Du. So we have I equals pi over 2, integral from 0 to infinity, u minus 1 over u squared plus 1, u plus 1 ln u du. So as I said before, whenever you see something that looks like this, we're going to immediately go to sub u equals 1 over, I don't know, v or whatever. So let's go ahead and make some more space again. I think that should work out for us, actually, surprisingly. It looks kind of nasty, but I think it will look good at the end. So we have u equals 1 over v, du equals negative 1 over v squared dv. So we're going to get pi over 2, integral from 0 to infinity, 1 over v minus 1 over, we're going to combine this v squared into this factor so that we just get v squared plus 1 again. We're going to get 1 over v plus 1, and then here we're going to get negative ln v dv. Multiply by v on the top and bottom. We're just going to get v plus 1 here, and then 1 minus v. And then we can use the negative sign, and we get the exact same integral as before. So helpful, right? Okay. So we're going to try another trick. Whenever you have x to the t minus 1 over ln x, this can be rewritten as the integral from 0 to t of x to the b db. And so we're going to go ahead and try and do that and exchange the order of integration and see what we can do there using that trick. So let's go ahead and make a lot more space for that. That's just basic differentiating under the integral sign. Really useful trick. And so whenever you see that, so we have v minus 1 here, so we can use that to our advantage in order to evaluate this integral right here. Sorry, it's taking me a while to erase all this stuff, but I hope you guys have enjoyed the video so far. Hopefully it hasn't gone too long, because I have a lot more problems planned to solve in the future. So we're going to have pi over 2, integral from 0 to infinity, integral from 0 to 1 of v to the b over v squared plus 1, v plus 1, db, dv. Exchange the order, pi over 2, integral from 0 to 1, integral from 0 to infinity of v to the b over v squared plus 1, v plus 1, db, or dv, db. I did not choose variable names very well here. Oh my gosh, dv, db. Okay, partial fractions, right? And then we're just going to use our formulas for that. So partial fraction sucks, but you know, you got to do it. So 1 over v squared plus 1 times v plus 1 equals a over v plus 1 plus bv plus d. Oh my god. Variable names are not good today. So we're going to get a v squared plus a plus b v squared plus bv plus cv plus c equals 1. So a plus c equals 1, b plus c equals 0, and a plus b equals 0. So let's go ahead and a minus c equals 0. So 2a equals 1, and a equals 1/2. C equals 1/2, and b equals negative 1/2. All right. So we're going to get, as I finish erasing all this crap, sorry, I don't really have time to edit this video, so you're going to have to listen to my little humming while I go ahead and erase the previous work on the integral. I'm quite certain that this will lead us to a good answer, though, so we shouldn't have too much to worry about. All right. So we have pi over 2 integral from 0 to 1 integral from 0 to infinity of 1/2 over v plus 1 times v to the b. This is going to prove to be a problem, isn't it? Well, let's see. Minus 1/2 v over v squared plus 1 times v to the b minus 1/2 v to the b over v squared plus 1 dv db. So for this one right here, we can evaluate this one right away. But for the other two, we're going to have to figure out another way to do it because v to the b is between 0 and 1, so both of those integrals actually diverge completely. So we're going to need to figure out a way to get them to converge. I think we can go ahead and sort of like cancel the terms. So if I go ahead and add, I just need to do some weird like division here. So I'm going to add, we have 1/2 v to the b. I'm going to add 1/2 v to the b minus 1 and subtract 1/2 v to the b minus 1. So this is going to just cancel, and it's going to become 1/2, all of this over v plus 1. We're just going to end up 1/2 v to the b minus 1 minus 1/2 v to the b minus 1 all over v plus 1. And then with this other one right here, I'm going to make it, okay, I'm going to do the same thing. So I need a lot more space to do this, but it should work out pretty nicely for us. Just need to be very, very careful with our work. Okay. So here we have v to the b plus 1. Okay, so we have 1/2 v to the b minus 1 minus 1/2 v to the b minus 1 over v plus 1 minus 1/2 v to the b plus 1 over v squared plus 1. Now here we're going to subtract 1/2 v to the b minus 1 and add 1/2 v to the b plus minus 1 right here. So we're going to end up here, we're going to have minus 1/2 v to the b minus 1. So this is going to cancel with this. Perfect. And so we're just going to end up with 1/2 v to the b minus 1. There has to have been a better way to do this, by the way. I just couldn't figure out what exactly that way was. So once we have all this reorganization, we're going to have a nice little integral. Just wait 1 second while I figure this all out. We are going to have pi over 2, integral from 0 to 1, integral from 0 to infinity, of minus 1/2 v to the b minus 1 over v plus 1 plus 1/2 v to the b minus 1 over v squared plus 1 minus 1/2 v to the b over v squared plus 1. Does that sound right to you guys? That sounds right to me. I'm going to hope that this is right, because otherwise, you know, I'm kind of screwed. So, and this is all dv. Now we're just going to use our integral formulas here. I've made videos in the past on a formula for this occasion, which is integral from 0 to infinity of x to the k over x to the n plus 1 dx equals pi over n cosecant of pi k plus 1 over n. And so that's what we're going to be using right here. I have plenty of proofs on that. I'm not going to go ahead and prove that right now, though. So let's go ahead and do that. So we're going to have pi over 2, integral from 0 to 1, of negative pi over 2 cosecant of b pi plus pi over 4 cosecant of b pi over 2 Alright, looking pretty good so far. And then we're going to have plus or minus pi over 4. That shouldn't look like this. Oh, I flipped the negative sign, didn't I? Oh, it doesn't matter. Cosecant of b plus 1 over 2 pi. So b plus pi over 2. B pi over 2 plus pi over 2. Okay, so this is a little bit nasty here. I think I may have screwed up a little bit. Wait, let's check. So in the limit, as b goes to 0, this doesn't diverge at all, but these two are going to go off to infinity. So in the limit, we have to make sure that they end up canceling with each other. I think they will because of the chain rule. So doing this integral is pretty straightforward. It's just annoying because we have to deal with so integral of cosecant x dx equals ln cosecant x minus cotangent x plus c, right? I'm just going to call this function f of x just to make things easier for us. So let's go ahead and do that. So we're going to have overall pi over 2 negative 1/2 f of b pi plus 1/2 f of b pi over 2. And then this one, instead of cosecant, we actually sort of have a secant here. Actually, I'll just leave it as it is, though. Minus 1/2 f b pi over 2 plus pi over 2, evaluated at 1 and at 0. Alright, so this is going to be a little bit nasty. Well, let's go ahead and solve this right here. So at 1, this one's going to be diverging and this one's going to be diverging. So we just have to hope that they sort of cancel with each other. At 1, they're both going to positive infinity, so they're not canceling. Alright, well, I'm going to admit that this problem has actually stumped me. I'm not entirely sure the right path to get to the answer here. I'm thinking maybe in the past I screwed up or I took a wrong path and I've gone down a bit of a rabbit hole here. Let's see how much time I have. I've already spent over an hour on this problem set, so I'm going to call it right here. I wasn't able to solve this one, but hopefully I'll come up with a solution sooner or later. But yeah, thank you guys for watching the video. I'm sorry I wasn't able to completely finish it, which is kind of awkward, but you know, it is what it is. Not every problem is going to be super easy to solve, so I don't want to waste too much time working on this problem. So yeah, I hope you guys enjoyed the video, and I'll see you next time when I hopefully solve some more math problems and you guys can see the solutions. So yeah, thanks for watching. Bye.